Hello everybody, welcome to the second video for section 3.9, and if you can believe it or not, this is our final video for this unit. Crazy how time flies when you're having fun, right? I certainly feel that way. Okay, so let's jump into it. Here we go. Nope. There it is. So if you recall, at the end of the last video, we learned a technique called logarithmic differentiation. And this is something we can use when our other differentiation rules don't seem to work, or if things are a little complex and maybe we could do it with a different differentiation rule, but it might be a little bit more work than we want to do. Okay, so we use it on this problem, and part of the reason we used it on this one, or we were able to use it on this one, is because notice in the exponent there, we have an x squared rather than just a number. So we couldn't just use our regular old power rule here. So logarithmic differentiation ended up being useful for us. Okay, so before we do another example of that, I just want to point out or remind you of some logarithm rules. So remember, your logarithm product rule is if you have a log of two functions being multiplied or two things being multiplied, you can write that as the sum of the logs of those things. And notice it's the log of the first plus the log of the second. If the two things inside the log are being divided, you can rewrite this as log of the first, or the top, excuse me, minus log of the bottom. And the other one we have that we used in that other last problem was the logarithm power rule, which just tells us that if we have something inside of our log, or if the thing inside of our log is raised to a power, we can move that power out to the front. Okay? So keeping those in mind, let's use those on this problem now. So here we have f of x equals x to the 7th times x minus 4 to the 6th over x squared plus 7 to the 4th. And first thing I will say is before we use logarithmic differentiation, you could use the quotient rule here because you have something divided by something. But then to take the derivative at the top, you'd have to use the product rule. Down there in the denominator, it looks like you have to use the chain rule and also the chain rule on the x to the minus 4th to the 6th. So it just seems like it might be a little more complicated. So we're going to try to simplify this. So remember, the first thing we do, just to simplify things, is to rewrite this as y equals x to the 7th over x minus 4 to the 6th, or times x minus 4 to the 6th, all over x squared plus 7 to the 4th power. And then we're going to take the ln of both sides, or the log of both sides. We'll do the ln. All right, yes, we definitely want to use the ln. Okay. And so then on the left-hand side, we now have ln of y equals, well, over here on the right, we have the ln of the top thing divided by, or over ln of the top divided by the bottom. So we have two things being divided inside the ln. So that means we can use that quotient property. So we can rewrite this as ln of x to the 7th times x minus 4 to the 6th minus ln of x squared plus 7, that whole thing raised to the 4th power. Okay, so just using that quotient rule there. Then notice that inside of this first natural log, we have two things being multiplied. So we can then use the product rule to break those apart. So I'm going to erase all of this and now rewrite the whole thing. So what we have is ln of y equals, we have ln of x to the 7th plus ln of x minus 4 to the 6th minus ln of x squared plus 7 raised to the 4th power. Okay? And what we can do now is, right, So we can use that exponent rule to move the 6 and the 4 out to the front. Okay. And then we can also go through and take the derivative of each of these things. Now we're going to take the derivative with respect to x, so we're really finding dy dx here. Okay, and you'll notice that with all of these on the right-hand side, we have functions within functions, so we're going to have to use the chain rule there. So if we go through and do this, well, for the ln of y, we'll have 1 over y as the derivative, since that's the derivative of ln, times dy dx, because we have the y in there. The ln of x to the 7th will be 1 over x to the 7th times, then we have to use the chain rule to take the derivative of the inside, so 7x to the 6th. Plus, here we move the 6 out to the front, it'll be times 1 over x minus 4 times the derivative of that, which is just 1, minus, we have the 4 times 1 over x squared plus 7 times the derivative of the inside, which is 2x. Okay, sorry, just checking my notes to make sure I didn't make any mistakes. Okay. And all of this stuff over here on the right-hand side, there's a little bit of simplifying that can be done. We can cross out some x's here. This can all be combined with the 6 times 1 over x minus 4 times 1, and then similarly here with this third term. And so when we do that, what we end up with then is 1 over y times dy dx equals, we will have 7 over x plus 6 over x minus 4 minus 8x over x squared plus 7. Okay, and then remember we have to isolate the dy dx here, which means we need to multiply both sides of this equation by y. Okay, so we'll have dy dx, or in this case, since we didn't start with a y, this is actually going to be f prime, equals, well, it's y times this thing, but as I just said, we didn't start with the y. Instead of y, we started with this thing here, and that's what y was equal to, right? So we have to plug that in for y. I'm going to erase this just because I need the room. So what we're going to end up with here is f prime of x, so the derivative, is going to be what that original function was, because that's going to take the place of y, over x squared plus 7 to the 4th times now all this stuff we have in parentheses here. So 7 over x plus 6 over x minus 4 minus 8x over x squared plus 7. Okay? And there we go. There is our answer. Isn't that fun? Man, these problems just keep getting more and more fun the more we get into this, the deeper we get in. Okay. So that is it for logarithmic differentiation. Now you have like 3 or 4 problems on your homework that ask you to use that. So I would suggest start working on those early. So in case you have any issues, you can try to figure out what those are. You can come visit me in an office hour to talk about them. All right, our last thing for this unit, and I believe this is actually from section 3.7. I don't think you'd find it in 3.9 in your book. But looking at derivatives of inverse trig functions. So we've talked about finding derivatives of sine, cosine, tangent, cotangent, cosecant, and secant. But what about the inverse trig functions? Okay, so things like this one up here, the y equals inverse sine of x. Well, I'm going to go through how to get the derivative of this. Now, I'll tell you right now, this process we're about to go through is not something I would ask you to do on a quiz or an exam, just so we see where this comes from. And the moral of the story here is you need to know what the final answer is, but you don't need to know this process. Okay, so first of all, we have y equals inverse sine of x. And remember, For those of you who took 142, Math 142 with me, you may remember we talked about this, and for any of you that have taken trig other places, hopefully you've seen this. So remember, the domains of the inverse trig functions are ratios, and the range, the things that they output, are angles, or angle measures, right? Usually in radians, which is different than something like, say, f of x equals sine of x. So here that's not an inverse trig function. So here the inputs, or the things in the domain, are angles, and then the outputs are ratios. Okay, so that's the difference between these two things. However, we're not dealing with that. We're dealing with inverse trig functions, right? In this particular instance. Okay, so we have this y equals inverse sine of x. So what that's telling us here is that we input some ratio x and it outputs some angle y. But knowing how trig functions work, what that's really telling us is that sine of y equals x, right? Because if x is the ratio and y is the angle, if we do sine of the angle, we should get the ratio, right? So we're just kind of rewriting that function. What I've written over here on the left is not any different, doesn't mean anything different from what the thing that we started with does. Okay, so now we're going to take the derivative here, and we're going to do this with respect to x. So we're going to do some implicit differentiation here. So take the derivative of sine of y, which we know that that is cosine of y. Right, derivative of sine is cosine. But there's that y in there, so by the chain rule, we have to multiply by dy dx. And then we take the derivative of the x on the other side with respect to x. That just gives us 1. Okay? So right now we have cosine of y times dy dx equals 1. We need to find dy dx because we're trying to find the derivative, right? So we need to isolate that. So we can do that by dividing by cosine of y on the left. Divide by cosine of y here. And so what we end up with then is that dy dx equals, I'll move this stuff here. So we have dy dx equals 1 over cosine of y. Now, for implicit differentiation, that was a totally fine answer for us to stay with. But, you know, it's kind of a little unsatisfying that we started with x as our input variable, and now we got something where y is the input variable, right? So we'd kind of like to not have to write it that way. So what we're going to do is we're going to use our good friend, the Pythagorean identity, which hopefully you remember or recall. So remember that it told us that if we have something like sine squared y plus cosine squared y, that was equal to 1, right? And that was a relationship we had between sine and cosine. So here we can subtract sine squared from both sides. Whoops, but not from there because that's on the same side. Okay, and so what that gives us, after these cancel, is cosine squared of y equals 1 minus sine squared of y. But in our problem up here, we don't have cosine squared, we have cosine, so we can undo the cosine squared here by taking the square root on both sides. And when we do that, then here on the left, the squared and the square root cancel out, so we have cosine of y equals square root of 1 minus sine squared. Okay, and in this case, I'm not going to worry about the plus or minus right now. So because of that, now we have something for cosine. We can go ahead and substitute that in up here. And you know what? I'm just going to clear this out. So we had dy dx was equal to 1 over cosine of y. And we just saw cosine of y is equal to square root of 1 minus sine squared of y. Okay. But you may remember a few minutes ago, based on this, we saw that x was equal to sine of y, right? Let me write that in a different color. All right, we had that on the board just a few minutes ago. Sorry, it's erased now. Okay, but it's kind of what we started our derivatives with. So because of that, we can make a substitution. Because sine of y equals x, we can take x and plug it in for sine of y here. And when we do that, what we end up with is dy dx equals 1 over square root of 1 minus x squared. And huzzah, there is our answer. Isn't that such a satisfying feeling? Good stuff, right? Okay, so as I said, that big long process we just went through is not anything you have to replicate on a quiz or a test, just so we understand where these formulas come from. And now that we have that, let me show you this. So these are the derivatives of all of the inverse trig functions. So inverse sine, as you see, derivative there is 1 over 1 minus x squared, or whatever the input variable is, squared. Inverse cosine is negative 1 over square root of 1 minus x squared, so very similar to the one for sine, except for it's negative. The derivative of inverse tangent is 1 over 1 plus x squared. Inverse cotangent, it's negative 1 over 1 plus x squared. And then the ones for inverse secant and inverse cosecant are kind of strange. So inverse secant, it's 1 over absolute value of square root of x squared minus 1. And then cosecant, or the inverse cosecant, is negative 1 over absolute value of x times square root of x squared minus 1. Okay. Now, I'll tell you right now, the ones that I would expect you to know or be able to recall for an exam or a quiz are these top 3. Okay, those are the ones that we use most commonly. Doesn't mean the other ones aren't important, but if you ever need to use them, you can look them up. The other thing I want to point out that you may or may not have seen before, when we see something like inverse sine, that is the same as if you see something like this. So arc sine of x and inverse sine of x, those mean the same thing. And it's similar for cosine, tangent, cotangent, secant, cosecant. If you see arc any of those, it means the inverse function. Cool. All right, that's all I have for now. Thank you guys for watching.